Hello everyone, welcome to the progress presentation. My name is Hawei, and today I will introduce you a very fascinating project that I'm currently working on. It's called AI-driven prioritization discovery for messenger RNA and lipid nanoparticles. First of all, I'll give you a bit of the brief background. We already know that mRNA vaccine has stepped on the world after the COVID-19 pandemic, but how that works. So that is a SARS virus. The blue part is a part of its RNA that contains the spike gene, which we need to learn it. So this blue part is the mRNA. Once we extract it, it could be delivered into cells and translate it into protein. Then our immune system, like T cells, could learn from it and recognize it. Since the mRNA are very fragile, it has to be packaged inside a lipid nanoparticles for successful delivery into the cell and for the protection. Here we need to introduce a new term called transfection efficiency. To make it simple, you can just think of that is a value that controls when and where you want to release the mRNA. So it affects the uptake, release, and toxicity of a lipid nanoparticle vaccine. However, the wet lab screening is very costly and slow. So here is where our artificial intelligence or data science could involve in. We can predict the transfection efficiency for a new molecular structure by training from it. About the research background, I have checked very few related works in last year. It's called Lion and Comet. There are not many modules has been done in this topic, but both of them are using very large data sets. However, it's hardly possible in real research circumstances because for each research group or each laboratory, they are targeting on different viruses and different cell lines. It's very hardly possible to get a large data that fit in those modules within a research cycle. So the problem comes to how could we build a reliable predictive models for lipid nanoparticle performance when the available data size is small and structurally complex. First of all, before we jump to the module, we'd like to thanks to the data provider and OCT validation support team from Chunxia, Professor Chunxia and Zhenwei. Thank you. Then, Professor Chunxia has provided a experimental dataset including 120 plus novel lipid candidates that haven't been published yet. So each of them are a part of the lipid nanoparticle packages. It looks like this. So that will be the dataset input that I'm dealing with. The green parts are the ligand group, the blue parts are the head groups, and the red-black parts are the tail 1 and tail 2. That will be all I have for the input for our module. Therefore, we need some feature engineering techniques to be able to build a reliable module. First, we would like to introduce the structure information because we already know for the lipid nanoparticle structures, even we added one more hydrogen or one more carbon atoms into the structure, it will perform totally different. So we will generate a Morgan fingerprints. It also called extended connectivity fingerprints, which contains, to make it simple, it's just a vector that contains the substructure information like rings, linkers, or functional groups based on its local atomic environments. Second of all, we have some physical or chemical descriptors in product level that are generated by RDK, including more weight or more log P structures, etc., etc. Once we have generating those features, we grab those features, we can build a baseline module. So tree-based modules like CatBoost or XGBoost or even random force are very powerful in bioinformatics. So we decided to try a tree-based module at the beginning or to become our baseline models. After the fine tuning, those are the fine-tuning results. After fine-tuning, we can see the catboost has the best R square. It's up to 0.65 percent, 0.65 something, and that is the y versus y hat plot. As we can see here, even though the graph looks not bad, but there are few points are flat. You can see that they are flat. That means that shows the module are guessing some structures using a average or something. That means the tree model is not capable to recognize all the patterns, and we don't want that. Then I have tried graph neural networks. Why? Because obviously, a molecule structure could be easily seen as a graph, right? Where the atoms can be nodes and the bonds can be edges. Then after resetting all this, we can get a adjacency matrix, and then we can represent the molecular structure as a graph with no directions inside. After we have presented it as a graph, we can introduce the neural network, graph neural network. That would be the graph neural network, one layer of the graph neural network. The function is here. That means each neighboring node's features are transformed by a weight matrix, then passing it to their neighbors, and normalized by their degree, and finally summing up. So we have choose a relatively new module called graph attention networks. We have built it as 2 layers and connect with a global mean pool, then pass them to a MLP to generate the final prediction. However, as you can see the result here, the CV cross-validation average are not good at all, and also the prediction versus the true value plot are very bad. They're flat. That means the module isn't learning anything. But why? Why is not working? First of all, it's likely because the sample size of our data set is very low, very small, and the graph are very large concatenated. And that means it contains so many information, then the neural network is overfitting it. So here, I come up with the idea that we can use the graph neural network embeddings, pass them to the catboost tree, and use them as a feature. Why? Because we already know GNN is gonna overfit our smart data, but we still want to preserve the molecular topology information and component interactions that we can grab them from the embeddings. The performance, the time is running, and the performance are here. We freeze the top 2 layers of the graph neural network, then pass them as a vector, concatenate them with those normal descriptors, then pass them all into the catboost pipeline. The performance comes to 0.67, which is outperformance the baseline, and this model hasn't been fine-tuned yet or optimized yet. I have a lot of things that I can try, and you can see the prediction graph. The flight has been eliminated a little bit, but it's not like perfect. So in the future, I have a few ideas that I would like to try. First of all, we know the GNN is gonna overfit, so maybe we can use a pre-trained large GNN model from large datasets to see will that help or not. And there are some advanced tabular deep learning modules come up, and we are dealing with tabular data. Once we have generated those features, our inputs could become tabular. And also we can try some active learning or autoencoders because we have limited data sets that I haven't tried yet. So once we have decided which model we are using, then we will predict a virtual laboratory, then pass those data sets, pass those predicted values into the wet lab that I'm collaborating with. They will do the OCT and to see how our module actually performs. Thank you for listening. I would like to clarify at the very end that all the data and results has been presented today is been done by myself. It is an individual project except the supervision and support from Dr. Henry Lee and the raw data that I collected from Professor Trinshak Zhou's team. Thank you.